Video, I want to discuss how we can derive the vertex form of a quadratic function from translations on the square function. The square function is the simplest of all quadratic functions. A quadratic function is simply a function of degree 2, meaning the highest power is a square. So the square function f of x equals x squared is the simplest quadratic function. So what we're going to do is translate this function. First of all, the square function is one that takes any input and squares to get the output. So for example, 0 squared is 0. 1 squared is 1. Negative 1 squared is also 1. 2 squared is 4, and negative 2 squared is also 4. We can have 3 or negative 3 squared give us 9, 4 and negative 4 squared give us 16, and what we get is what we call a parabola, which is curved on the bottom here. So this is our parabola. This parabola, we say, opens up because the arrows are pointing up, and that's where it is open. The lowest point, right here, the point 0, 0, that is called the vertex. So the vertex is the lowest point on a parabola that opens up. Now, if we take the square function and negate it, so for example, if we have g of x equals a negative x squared, that simply makes all the outputs negative, so now the function opens down because all the outputs are negative. And at this point, when we have an upside down parabola, then we see the vertex is a maximum. Whereas before we said or saw that the vertex was a minimum. What we're going to do is take this parabola, we're going to move it up and down and side to side so that the vertex changes. So let's consider the example where we take the square function and I am going to move it to the right 3 units, and I'm going to move it up 2 units. I'm also going to make it fatter, meaning it increases at a slower rate, and to do that I can multiply it by a fraction less than 1. And I want to turn it upside down, so that would make it negative. So I'm going to start with this square function, and I am going to shift it right 3 units. Then I will shift it up 2 units. I want to make it fatter or have it increase more slowly by multiplying it by 1/3. This will have it increase 3 times more slowly. And then I am going to make it negative so it opens upside down. So I want it to open down. So first, let's look at what happens when we shift it 3 units to the right. So we start off with our square function, and then we want to go 3 units to the right. So now that the vertex is at the point 3, 0, but otherwise the shape has not changed. So it has the same shape, it's just been shifted 3 units to the right. So what we've done is we've moved the x coordinate 3 units to the right. So let's see. We have f of x equals, and now we need to decide, did we add or subtract 3 units to get it over here? Well, note that the y-coordinate is 0. So in order to have a y-coordinate of 0, it must have been subtracted 3 units. Because that way, when I evaluate the function at 3, I do indeed get 0 for the output, so that the point 30 is on this function. So by shifting it right 3 units, I have x minus 3 squared. Now let's shift it up 2 units. And that's in addition to the 3 units here. So now I move it here. I still have the same basic shape, but we see now that the vertex is at the point 3, 2. So to get this up 2 units from 0, we have to add 2. Great. So what we see so far is, if I were to call the vertex with the general coordinates h, k, I see that shifting h units to the right and 2 units up, so I'm more general, I mean k units up, then we end up with f of x equals parentheses x minus h squared plus k. So this is part of the vertex form, but it is not entirely finished. Because what we want to do next is to multiply by 1/3 so that it becomes a flatter parabola. So here we are finally actually changing the shape. We want it to be wider, and we actually want it to be 3 times wider. So that means I'm going to multiply by 1/3, and this coefficient here then is a. So we have a times the quantity x minus h squared plus k, and that is our final vertex form of a quadratic function. Now, for my example, I'm doing one more thing. I wanted to open down. And as we saw before, to open down, we need to negate the squared term. So I'm going to put a negative in front. So now what I have here now is a function in vertex form that looks like f of x equals negative 1/3 times the quantity x minus 3 squared plus 2. F of x equals negative, because it opens down, 1/3, because it's 3 times as wide, or it is increasing 3 times more slowly as a square function, times the quantity x minus 3, because it was shifted 3 units to the right, and that quantity is squared, it was shifted up 2 units. So f of x equals negative 1/3 x minus 3 squared plus 2, and that corresponds in general to the vertex form f of x equals a times x minus h squared plus k. And there we have vertex form of a quadratic function. And we can see that it was just easily obtained or derived from transformations or translations, vertical and horizontal translations. Then we multiplied by a constant, in this case to slow its growth. If we wanted it to be skinnier so that it was increasing more quickly, we'd have multiplied by a number bigger than 1, such as if we wanted it to grow 3 times faster, we'd have multiplied it by 3. So once we have vertex form, then we can see how easy it is to graph a function because we can read off the vertex immediately. So just going the other way around, we've already saw what this graph looks like because we actually did the shifting before we got the function. But if we were given the function first, right, if we were given the function f of x equals negative 1/3 x minus 3 squared plus 2, we would immediately have seen that the vertex was the point 3, 2. And because the leading coefficient here, this a, is called the leading coefficient, because the leading coefficient was preceded by a negative, so it was less than 0, then we saw that it opened down, so this opens down. And right away, we would have 1, 2, 3, 1, 2, vertex, opens down, though I wouldn't know exactly what these intercepts were, or if I drew it maybe like this, I wouldn't know where the y-intercept is either. So what's missing then for a more accurate graph, if I were starting from the function, are these intercepts here. What are these intercepts? And we didn't even discuss that before. So how do we find these intercepts? Well, we know that intercepts are where we cross the axes. So if we want to find, say, the y-intercept, when the graph crosses the y-axis, that's where the value of x is 0. So to find the y-intercept, we simply evaluate the function at 0. So negative 1/3 times 0 minus 3 squared plus 2. So 0 minus 3, negative 3 squared is 9. And so we have f of 0 equals negative 1/3 times 9 plus 2. Negative 1/3 times 9 is 9 divided by negative 3, which is simply negative 3. Add the 2, and we have negative 1. So we see that it has a y-intercept at the point 0, negative 1. What about x-intercepts? Well, whereas the y-intercept occurred when x is 0, the x-intercepts occur when y is 0. So we end up setting the function f of x, which is y, equal to 0. So let's find those x-intercepts by setting our function equal to 0. So our function f of x equals 0. And that is a negative 1/3 times the quantity x minus 3 squared plus 2. In order to solve this, we're going to use the square root method because there is a perfect square right in the function. When you're in vertex form, we have this x minus 3 squared term. So let's isolate the squared part by first subtracting 2 from both sides. That will give us negative 2 equals negative 1/3 times the quantity x minus 3 squared. Now we need to get rid of the negative 1/3, so we will multiply both sides by negative 3. So on the left-hand side now, we have a 6 equals x minus 3 quantity squared, because negative 3 times negative 1/3 becomes 1, cancels out. Now, this is where we get the term square root, method, because we want to take the square root of both sides to undo the squaring. So if I take the square root undoes the squaring, and I'm left with the x minus 3 on the right. On the left, I take the square root, but because both positive and negative values when squared will give me a positive value, I need both the plus and the minus versions of the square root of 6. So we have plus or minus root 6 equals x minus 3. And finally, we solve for x by adding 3 to both sides. So we see that x equals 3 plus or minus the square root of 6. If we want to think in terms of like decimal approximations from my calculator, I can find that the square root of 6 is approximately 2.45 to 2 decimal places. So I can write x equals 3 plus or minus 2.45. So our x-intercepts are equidistant from 3, where 3 is the x-coordinate of the vertex. Therefore, it's symmetric about this line. And so the line x minus 3 here, that vertical line, is the axis of symmetry. So in general, when we are in vertex form, then we see that the h, because remember vertex form has x minus h squared plus k, this h, x equals h, is our axis of symmetry. Let's go ahead and graph what we have so far. So we know that the vertex is at 3, 2. We already discussed that. We know that it's a little fat. It opens down. And we saw that the y-intercept was at negative 1. I did not note that earlier. Well, I noted it, but I didn't write it down. So let me write it down here when I finish erasing. So we had found that the y-intercept was the point 0, negative 1. And if we graph this, we have 0, negative 1. our axis of symmetry, 1, 2, 3, is at x equals 3. The vertex is always on the axis of symmetry, and that's the point 3, 2. It opens down, and it passes through this -1. And because of symmetry, we can find another point here that is 3 units from the axis of symmetry and 1 unit down to mirror the y-intercept, right, to draw our graph. Now the x-intercepts are equidistant from this axis of symmetry x equals 3. We're actually moving 2.45 units to the right and to the left. So 1, 2.45, okay, takes us to 5.45. And then here, 1, 2.45 takes us to 0.55. So here are the intercepts, where this distance here was the root 6, or the 2.45 units. So we're adding and subtracting 2.45 to the axis of symmetry here to find these x-intercepts. So that is the vertex form. We derived from translations to get the equation. Then, with the equation, we actually found the y-intercept by simply evaluating the function at 0. We found the x-intercepts by setting the function equal to 0 and solving for x, where we see that we are equidistant from the axis of symmetry on which the vertex lies, and we get this nice graph. So in my next video, I am going to talk about converting our vertex form to standard form and how we can find the vertex and the intercepts from standard form. So next video we'll discuss standard form. Thank you for listening and watching. I hope this was useful.